Welcome! In today's session, we'll dive into problem number 1403, titled Minimum Subsequence in Non-Increasing Order. We'll walk through the problem statement, explore the key concepts, and evaluate different approaches to solve this challenge. Let's get started. The goal of this problem is to find a minimum subsequence from the given array of integers, where the sum of the subsequence is strictly greater than the sum of the elements not included in it. Additionally, if there are multiple valid subsequences, we prioritize the one with the maximum total sum. If there are still ties, we select the subsequence with the smallest length. It's worth noting that a subsequence is formed by deleting some or no elements from the array while maintaining the order of the remaining elements. The input to this problem is an array of integers, constrained to have a length between 1 and 500, with each element having a value between 1 and 100. The output is a list of integers that represents the minimum subsequence satisfying these conditions. For example, consider the array nums equals 4, 3, 10, 9, 8. A valid output is 10, 9. The explanation goes as follows. The sum of the subsequence, 10, 9, is 19, which is strictly greater than the sum of the remaining elements, 4, 3, 8, which amounts to 15. Out of all possible valid subsequences, 10, 9, has the maximum total sum while also being of minimum length. This satisfies all the requirements outlined in the problem statement. Now, let's look at another example. For the input array nums equals 4, 4, 7, 6, 7, the output is 7, 7, 6. Here, the subsequence 7, 7, 6 has a sum of 20, which is strictly greater than the sum of the remaining elements, 4, 4, which equals 8. This subsequence achieves the maximum total sum while satisfying the minimum length condition. Another case to consider is when the input is nums equals 6. Since the array contains only one element, the only valid subsequence is 6 itself. When the input array contains only one element, as in the case of nums equals 6, the subsequence 6 is the only possible and valid solution since it already fulfills the condition of having a sum greater than the sum of the remaining elements, which is 0. Moving on to constraints, the problem specifies that the length of the array can range from 1 to 500, and each element will have a value between 1 and 100. For edge cases, if the array contains a single element, the subsequence is simply the array itself. If all elements have the same value, the solution will depend on finding the smallest subset that meets the condition. Lastly, since the array can be large, it's important to ensure the solution is computationally efficient. To solve this problem, we first considered the brute force approach. The intuition here is straightforward: generate all possible subsequences of the array, calculate their sums, and check if the sum of a subsequence is strictly greater than the sum of the remaining elements. Among all valid subsequences, we would choose the one with the smallest size. However, generating all possible subsequences is computationally expensive because it takes 2 to the power of n time, and then checking the sums for each subsequence adds an additional n per subsequence. This results in an overall time complexity of 2 to the power of n*n, which becomes infeasible for even moderately large input sizes. While conceptually simple, this approach is impractical for competitive programming or real-world scenarios. Instead, we turn to a more efficient solution using a greedy approach. Here, the key insight is that the largest numbers in the array contribute the most to the subsequence sum. By prioritizing these larger numbers, we can construct the desired subsequence more efficiently. This strategy involves sorting the array in descending order, then iterating through the sorted array to greedily pick elements until the condition is met. Let's explore this approach in detail. The greedy approach offers a significant improvement in efficiency. First, we sort the array in descending order, which takes n log n. Then, we iterate through the array to construct the subsequence, dynamically keeping track of the total sum of the array and the sum of the subsequence. The idea is to stop adding elements as soon as the sum of the subsequence exceeds the sum of the remaining elements. This iteration step takes n. Together, the overall time complexity becomes n log n, which is far more manageable than the exponential complexity of the brute force approach. This method is efficient and scales well for large input sizes, making it suitable for competitive programming and real-world applications. The greedy strategy ensures that we construct the minimal subsequence size while meeting the required condition, which is why it is the preferred solution here. We ultimately chose the greedy approach because of its balance between efficiency and simplicity. The key observation is that the largest numbers in the array have the greatest impact on the subsequence sum. By sorting the array in descending order, we can ensure that we prioritize these larger numbers first, allowing us to meet the condition where the subsequence sum is greater than the remaining sum using the fewest elements. The brute force approach, while theoretically correct, is computationally prohibitive due to its exponential time complexity, making it unsuitable for practical use. In contrast, the greedy approach runs in n log n, making it a robust choice for both small and large datasets. One of the critical aha moments in this solution is realizing how sorting the array simplifies the problem into a straightforward greedy selection process. While alternatives like using a maxheap could also achieve the same time complexity, sorting is simpler to implement and avoids the overhead of managing additional data structures. By focusing on simplicity and efficiency, the greedy approach stands out as the optimal solution for this problem. It leverages the natural properties of the array, prioritizing larger numbers to efficiently construct the minimal subsequence. This method balances performance with ease of implementation, making it an ideal choice for solving the problem effectively. The problem requires us to find the smallest subsequence of an array such that the sum of the selected subsequence is strictly greater than the sum of the remaining elements. To solve this, we first need to divide the array into two parts. One part is the subsequence we are building, and the other part is the leftover elements. The goal is to make the subsequence sum larger than the remaining sum using the fewest elements possible. A greedy approach works well here, where we prioritize taking the largest elements first. This is because larger elements contribute more to the subsequence sum and help us meet the condition faster. To make this approach efficient, the first step is to sort the array in descending order. For example, if the input array is 4, 3, 10, 9, 8, sorting it gives 10, 9, 8, 4, 3. This ordering simplifies the process of selecting the largest elements one by one, which minimizes the size of the subsequence while ensuring the condition is met. Once the array is sorted, we calculate the total sum of all the elements in the array. This value, which we'll call total_sum, allows us to track the sum of the elements not yet included in the subsequence. For instance, if the sorted array is 10, 9, 8, 4, 3, the total sum is 34. Next, we initialize two variables, subsequence_sum to keep track of the sum of the selected subsequence, starting at 0, and remaining_sum to track the sum of the leftover elements, which initially equals total_sum. We also create an empty list called subsequence to store the elements we select. Then, we iterate through the sorted array. For each element, we add it to subsequence_sum, subtract it from remaining_sum, and append it to the subsequence list. After each addition, we check if the subsequence_sum has become strictly greater than remaining_sum. If this condition is satisfied, we stop iterating. This ensures that we only take as many elements as necessary to meet the problem's requirements. To illustrate the process, consider the sorted array 10, 9, 8, 4, 3, with a total sum of 34. In the first iteration, we select 10, adding it to the subsequence. This makes the subsequence_sum equal to 10 and reduces the remaining_sum to 24. In the second iteration, we add 9 to the subsequence, increasing the subsequence_sum to 19 and decreasing the remaining_sum to 15. At this point, the subsequence_sum of 19 is strictly greater than the remaining_sum of 15, so we stop. The final subsequence is 10, 9. This demonstrates the key insights of the algorithm. Sorting the array in descending order ensures we efficiently select the largest elements first, and stopping early when the condition is met avoids unnecessary computations. This greedy approach guarantees that the subsequence is as small as possible while satisfying the problem's requirements. To implement this solution, we rely on a few simple yet effective data structures. Sorting is performed directly on the array to arrange the elements in descending order, which facilitates the greedy selection process. The running sums, subsequence_sum and remaining_sum, are managed using basic variables that dynamically update during the iteration. The selected subsequence is stored in a list, which is returned as the result. Analyzing the algorithm's complexity, sorting the array requires O, n asterisk log, n, time, and iterating through the array takes O, n, making the overall time complexity O, n asterisk log, n. The space complexity is O, n, primarily due to the storage of the subsequence. It's also important to consider edge cases. For a single element array, such as 5, the result is simply 5, since the condition is automatically satisfied. If all elements are equal, like 4, 4, 4, 4, the algorithm will pick elements until the condition is met. If the input array is already sorted in descending order, the algorithm still functions correctly. Finally, the algorithm handles large arrays efficiently due to its logarithmic factor in the sorting step, ensuring scalability for larger inputs. This code solves the problem of finding the smallest subsequence in non-increasing order such that the sum of the subsequence is strictly greater than the sum of the remaining elements in the input array nums. Step-by-step explanation. 1. Sorting the array asterisk. The first step is to sort the array nums in non-increasing, descending, order. This ensures that we can pick the largest elements first to quickly maximize the subsequence sum. 2. Calculating total sum asterisk. We compute the total sum of the array to help us determine when the subsequence sum exceeds the remaining sum. 3. Initializing variables asterisk. We initialize subsequence underscore sum to 0 to keep track of the sum of the chosen subsequence. An empty list result is used to store the elements of the subsequence. 4. Building the subsequence asterisk. We iterate through the sorted array. For each number, add it to the subsequence underscore sum. Append it to the result list. 5. Checking the condition asterisk. After adding each number, we check if the subsequence underscore sum is greater than the sum of the remaining elements, total underscore sum, subsequence underscore sum. If true, we return result as the solution since the condition is met. 6. Returning the result asterisk. If the loop completes without returning early, unlikely due to the problem constraints, the final result list is returned. This is a safeguard for edge cases. Keynotes. Sorting the array in descending order ensures we pick the largest numbers first to minimize the subsequence size. The condition subsequence underscore sum total underscore sum subsequence underscore sum guarantees that the subsequence sum is strictly greater than the remaining sum. This approach is efficient with a time complexity of O, n log n, dominated by the sorting step. The subsequent iteration over the array is O, n, making the solution optimal for this problem. Here, we begin by importing the necessary Java utilities. Inside the solution class, we define the method minSubsequence, which takes an array of integers as input. The goal is to find the smallest subsequence of numbers such that the sum of this subsequence is greater than the sum of the remaining numbers. First, we sort the input array in ascending order using arrays.sort. Since we need the numbers in descending order, a custom helper method, reverseArray, is called later to reverse the array. After sorting, we calculate the total sum of all elements in the array by iterating through it in a simple loop. Next, we initialize two variables, subsequence sum, which will track the sum of the numbers we add to the subsequence, and result, an ArrayList to store the elements of the subsequence. Then, we iterate over the sorted array in descending order. For each number, we add it to subsequence sum and also append it to the result list. We check if the current subsequence sum exceeds the sum of the remaining elements in the array. If this condition is met, we break out of the loop, as we found the required subsequence. Once the loop is exited, the result list contains the desired subsequence. This list is then returned as the output of the minSubsequence method. Additionally, we define the helper method reverseArray, which is used to reverse the order of the numbers in the array after it has been sorted in ascending order. The method takes the array and its length as parameters. It swaps elements from the start and end, moving inward, effectively reversing the array in place. This ensures that we can process the numbers in descending order without requiring additional sorting logic. Together, these components allow the solution to efficiently compute the minimum subsequence with the required properties, while maintaining clarity and simplicity in the implementation. To solve this problem, we start with an example where the input array is nums equals 4, 3, 10, 9, 8. The first step is to sort the array in descending order so that the largest elements come first. After sorting, the array becomes nums equals 10, 9, 8, 4, 3. Next, we initialize some variables. The total underscore sum is the sum of all the elements in the array, which is 34. We also set subsequence underscore sum to 0, as this will track the sum of the elements we select, and result is initialized as an empty list to store those elements. Now, we iterate through the sorted array. In the first iteration, we add the largest element, 10, to the result list, making it 10. We also update subsequence underscore sum to 10. At this point, we check whether subsequence underscore sum is greater than the sum of the remaining elements, which is total underscore sum subsequence underscore sum. Here, 10 is not greater than 24, so we proceed to the next iteration. In the second iteration, we add the next largest number, 9, to the result list. Now, result becomes 10, 9, and subsequence underscore sum is updated to 19. We check again whether subsequence underscore sum is greater than the sum of the remaining elements. This time, 19 is greater than 15 because 19 greater than 34 19. Since the condition is met, we stop iterating and return the result, which is 10, 9. This subsequence has a total sum of 19, which is greater than the sum of the remaining elements, 15. Moving to the next example, the input array is nums equals 4, 4, 7, 6, 7. First, we sort the array in descending order. After sorting, it becomes nums equals 7, 7, 6, 4, 4. With the sorted array nums equals 7, 7, 6, 4, 4, we initialize the variables. The total underscore sum is calculated as 28 by summing up all the elements. We set subsequence underscore sum to 0 and start with an empty result list. In the first iteration, we add the largest number, 7, to result. Now, result is 7, and subsequence underscore sum is 7. Next, we check whether 7 is greater than 21, the remaining sum. Since this is false, we move to the second iteration. Here, we add another 7 to the result list, making it 7, 7, and update subsequence underscore sum to 14. Again, we check whether 14 is greater than 14, and it is not. In the third iteration, we add 6 to the result list. Now, result becomes 7, 7, 6, and subsequence underscore sum is updated to 20. This time, 20 is greater than the remaining sum of 8, so we exit the loop. The final output for this example is 7, 7, 6. This subsequence has a total sum of 20, which is greater than the sum of the remaining elements, 8. Now, for our third example, the input array is nums equals 6, 6, 6, 6. As usual, we start by sorting the array in descending order. Since all the elements are identical, the sorted array remains nums equals 6, 6, 6, 6. Moving forward, we initialize the variables. The total underscore sum is 24, calculated by summing all elements. We set subsequence underscore sum to 0 and initialize result as an empty list. In the first iteration, we add the first 6 to result. This makes result equals 6, and subsequence underscore sum is updated to 6. We then check whether 6 is greater than 18, and since it is not, we continue. In the second iteration, we add another 6 to result, which updates it to 6, 6. The subsequence underscore sum becomes 12. We check whether 12 is greater than the remaining sum of 12, and this condition is still false. In the third iteration, we add another 6 to result, making it 6, 6, 6, and increase subsequence underscore sum to 18. This time, 18 is greater than the remaining sum of 6, so we exit the loop. The final output for this example is 6, 6, 6. This subsequence has a total sum of 18, which is greater than the remaining sum of 6. To understand the time complexity of this solution, we need to break it down into its key steps. First, the input array is sorted in non-increasing order using the sort function with the reverse equals true parameter. Sorting an array has a time complexity of O, n log n, where n is the number of elements in the array. This step is the most computationally expensive part of the algorithm. Next, we calculate the total sum of the elements in the array using the sum function. This requires iterating through all n elements, giving it a time complexity of O, n. Finally, we iterate over the sorted array in a loop. In each iteration, we add the current element to the subsequence sum and append it to the result list. In the worst case, this loop runs for all n elements, so this step contributes another O, n, to the time complexity. While iterating through the sorted array, we also check the condition if subsequence_sum total_sum subsequence_sum to determine whether the subsequence satisfies the problem's requirements. This condition involves basic arithmetic and a comparison, both of which are constant time operations. Since this check is performed during each iteration of the loop, it contributes O(1) per iteration, or O(n) in total. Combining all these steps, the dominant term in the time complexity is the sorting step, which is O(n log n). The sum calculation and iteration steps, each contributing O(n), are asymptotically smaller than the sorting step. Thus, the overall time complexity of the solution is O(n log n). Now, let's analyze the space complexity of the algorithm. First, the input array is sorted in place, meaning no additional memory is used for this operation. This contributes O(1) to the space complexity. Next, we create a new list called result to store the subsequence. In the worst case, this list could contain all n elements from the input array, which contributes O(n) to the space complexity. Additionally, we use a few auxiliary variables, such as total_sum, subsequence_sum, and number, to hold intermediate values during computation. These variables require a constant amount of memory, contributing O(1) to the space complexity. Therefore, the overall space complexity of the algorithm is dominated by the result list, making it O(n). The total space complexity analysis highlights that the result list, which can contain up to n elements, is the primary contributor, resulting in O(n) space usage. Additionally, the algorithm's efficiency can be contrasted with a brute force approach. A naive solution would generate all possible subsequences of the input array, calculate the sum for each, and then check the condition for each subsequence. This approach would require O(2 to the power of n) time complexity, as there are 2 to the power of n possible subsequences, and O(n) space to store one subsequence at a time. Comparatively, our solution drastically reduces the time complexity from O(2 to the power of n) to O(n log n), making it much more efficient while maintaining the same O(n) space complexity. Finally, we can assess the algorithm's performance across different scenarios. In the best-case scenario, the subsequence condition is satisfied after selecting only a few elements. However, since sorting still dominates, the time complexity remains O(n log n). In the average case, the condition is met after processing about half the elements, and again, sorting ensures the overall complexity stays O(n log n). Even in the worst case, where all elements are required to satisfy the condition, the time complexity remains O(n log n) because of the sorting step. The mathematical proof reinforces this, as sorting using timsort is O(n log n), while summation and iteration, both O(n), are asymptotically smaller. The space complexity, dominated by the result list, is consistently O(n) across all cases. This guarantees that the algorithm is efficient and scalable for a wide range of input sizes. Common mistakes in solving this problem often stem from overlooking critical details. For example, when dealing with edge cases, arrays with no elements or just one element are easy to miss but can cause runtime errors like index out-of-bound exceptions. To handle this, it's crucial to add explicit checks for these cases at the start of your solution and include test cases to validate them. Another common pitfall is ignoring the constraints on input size. If you attempt a brute force solution without considering the scale of the input, such as arrays with more than 10,000 elements, your approach may become inefficient or even fail to execute within the time limits. Always analyze your algorithm's time complexity to ensure it meets the constraints. Additionally, errors can arise when partitioning the subsequence from the remaining elements. For instance, dynamically tracking sums or using indices incorrectly can result in miscalculations. To avoid this, use descriptive variable names and carefully double-check your logic for summing and partitioning the array. Now, another mistake to watch out for is overcomplicating the brute force approach. Instead of explicitly generating all possible subsequences, which can be computationally expensive, focus on leveraging properties like prefix sums or making greedy choices to simplify the implementation. It's about working smarter, not harder. Similarly, misunderstanding greedy strategies can lead to incorrect solutions. Assuming that a greedy algorithm will always work without proving its correctness is a common error. For instance, sorting the array in descending order and picking the largest elements might feel intuitive, but you should validate why this approach works by showing it leads to the optimal solution. This ensures your solution is both accurate and efficient. When approaching this problem in an interview, there are a few key insights to keep in mind. First, pattern recognition is essential. Problems like this often involve subsets, partitions, or prefix sums, so identifying when sorting or greedy methods are applicable is crucial. Next, consider the concept of optimal substructure. If the problem can be broken into smaller, solvable subproblems, techniques like dynamic programming or greedy algorithms may be appropriate. During the interview, it's also important to communicate your assumptions clearly. For example, clarify constraints with your interviewer to avoid adding unnecessary complexity to your solution. Additionally, always discuss time complexity trade-offs, such as comparing the inefficiency of brute force approaches, which might have exponential time complexity, with more optimized solutions like O(n log n) or O(n). Finally, don't overlook space complexity. Be prepared to explain how your solution minimizes memory usage, especially if you're using additional arrays or data structures. To deepen your understanding, let's connect this problem to similar ones. For instance, LeetCode 1403, which focuses on finding a minimum subsequence in non-increasing order, uses a similar greedy strategy to partition the array. LeetCode 1753, another related problem, requires balancing sums to maximize the score through a greedy approach. Meanwhile, LeetCode 416 and 698 involve partitioning arrays into subsets with equal sums. These problems demand more advanced techniques like dynamic programming or even backtracking. Looking at alternative approaches for solving this problem, the brute force method involves generating all possible subsequences. While simple, it's impractical for large inputs due to its O(2 to the power of n) time complexity. However, it can be useful for small cases or as a way to validate the correctness of a more optimized solution. On the other hand, the greedy approach stands out for its efficiency. By sorting the array in descending order and iteratively selecting elements until the condition is met, you achieve an O(n log n) time complexity, which is much more scalable. This method is intuitive, but remember that its correctness must be proven to ensure it always leads to the optimal solution. For more complex variations of this problem, dynamic programming could be a viable approach. By using a DP table to track possible sums for subsets, you can solve partitioning problems efficiently. The time complexity of this method is O(n*target_sum, where target_sum represents the desired sum you're trying to achieve. While dynamic programming is powerful, it comes with higher space requirements, typically O(target_sum). This trade-off makes it less memory efficient than the greedy approach but invaluable for problems that require more precise control over subset sums. Understanding these advanced techniques gives you a broader toolkit for tackling similar challenges in the future. To wrap up, we reviewed the key algorithm, its efficiency, and the importance of greedy approaches for solving optimization problems like this. Keep practicing these techniques to strengthen your problem-solving skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!